So, we're going to continue our series on astronomical measurements. And in this video clip, we're going to cover the specifics of how we find distance using stellar parallax. So let's just think for a moment on how we actually find distances to our celestial objects that we see in the night or day sky. So this is a daunting question, and there's a lot of science behind it. So the techniques have been proved decade after decade. So we look at something called the cosmic distance ladder. This is the technique that astronomers rely upon to build distances that are close to us that we've got accurate measurements with to distances further and further out. So there's a lot involved in building this cosmic distance ladder, this series of measurements to determine distance in our cosmos, to celestial objects in our cosmos. So let's just consider observing on the surface of our confinement of Earth, right? So we have nearby objects, such as solar system objects, and then we have further out objects, nearby stars, and then we have further stars, and then even like the first galaxies, and then really far, far out, and galaxies far, far away. Okay, we build this ladder of measurements all the way up to the edges of our observable universe. So, nearby celestial objects, well, what do? Well, we rely upon geometry, Kepler's laws. There's 3 laws of motion, and combine that with radar. Yes, in the modern day we have radar. So if we want to find the distance to the moon, all we do is we take laser light, we bounce it off the surface of the moon, and we time it, and we figure out how long it takes to come back. We use the speed of light and that time to find the distance. And we use a simple distance equals rate times time, where the rate is the speed of light. The time is what we measure. And then we get a good, accurate distance on the moon. Okay? Kepler's laws, we look at the elliptical orbits, and we look at how the period of rotation, revolution, going around the sun is related to how far out from the sun it is. That's the 3rd law I'm quoting there. So we use the orbital mechanics within Kepler's laws, and we use the ratio of different orbits in our solar system combined with the radar values to get precise measurements in our solar system. Okay, now the second one is the one we're going to look at, and this is called stellar parallax, and I'll go into more detail on that. But what we'll do is a little overview, we look at the apparent shift. So we'll see the nearby stars move slightly with respect to the background stars due to them being closer to us, and the fact that we are orbiting the sun and we're taking measurements from different positions in our orbit around the sun, or our revolution around the sun. Okay, so that's stellar parallax. The 3rd main method is using standard candles. And the idea behind this one with standard candles is we look at the brightness. So we take a look at how bright the objects appear to us, and then compare them to the models of where they are in their stellar evolution, where they should be with their luminosity, and we equate that with the distance. So we use apparent magnitudes, luminosity, and distance. We use those relationships to figure out the distance. So there can be some problems that arise from that, because it's not always well known what the exact luminosity is. But the idea is we know the further an object away from us it is, the less photons will receive, the less light will receive off that object. Okay, so we take a look at what it appears, what its brightness appears to us, and how much light it's actually putting off, and we gauge that to the distance. So it's a little more complex, subject for another video clip. So standard candles use brightness or magnitude, luminosity with distance, and our knowledge of how luminous these stars should be in their evolution. And the fourth main method is when we get further out, so nearby we're looking at within 1,000 kiloparsecs for the nearby stars, but as we go further and further out to galaxies further away, we start looking at how the light is shifted. We look at Doppler shifts. And the idea is, since the birth of the universe, the further out objects are accelerating, are moving away from us at a greater rate than the objects closer to us. So we use this a lot for galaxies. So the further away a galaxy is, the more red shifted the light would be. The closer it is to us, if it's coming towards us, it would be blue shifted. So further away, galaxies will be more red shifted. So we look at red shifts, and these are shifted light spectrums. The shifted light spectrum of moving objects, of receding objects, such as galaxies. And of course, this is what Edwin Hubble did in the 1920s. He saw that galaxies further away were moving faster and faster away from us because he saw the redshifts were greater, and this provided the evidence that the universe was expanding. Okay, and evidence that backed up the Big Bang. So those are the main methods, but other ones that are out there, and there's more. So note there's others that are building on. We do a lot of work with variable stars and use those to gauge distances. We look at supernova. There's a lot other formal techniques involved, but it's something to look up. You can look up the cosmic distance ladder to get some of these other sophisticated methods that are building on our knowledge of the distance. Okay, let's look at stellar parallax, but first let's just understand what parallax means in general. And there's some great experimentation you could do on your own to witness this phenomena that we use to measure distances to stars. So parallax is this apparent shift due to changing your line of sight when viewing an object, okay, with respect to a background. So we have this difference in position when we're looking at it from two different lines of sight. And here is an experiment you could do. Find a sign or a title. For instance, let's go ahead and look at this word measurements right here. Okay, so if you're going to look at measurements, we're going to look at this title. And the experiment is, let's go ahead and cover, let's first set ourselves in front of measurements, go a few meters in front of it. Okay, take your finger and center it in front of the word, and then cover up your left eye and look at your finger. Uncover your left eye and then cover your right eye and look at your finger. And you can see that the position of your finger changes with respect to the wording of the word measurements. Okay, and you can do that with anything. You could just take your finger and put it in front of a sign, cover your left eye, uncover it, and then cover your right eye. And it seems like there's a shift with respect to the background of your finger. Well, that's how stars work too. And the idea is that here when we have our eyes, when we have one eye uncovered and we're looking at, let's say our nearby finger right here. Okay, here's our sight. We're going to see it. Here's our line of sight with respect to this background. And then we cover this eye up and uncover this eye. And we see a different background, our finger in front of a different background. Okay, and this is our line of sight here. There's some splendid geometry involved. Okay, and that's what we're doing. So you do a finger in front of sign. Try it out. Okay. Now, moving on, let's go ahead and look at stellar parallax. Well, the same idea. Okay, in this case, what we're doing is we're looking at the slight shift in position of nearby stars with respect to the background stars. Okay, so stellar parallax, this definition we could fine tune. We have the same apparent shift of this nearby star with respect to the background stars when we're viewing it from two different positions in Earth's orbit. So it's tied into our average distance from the sun, 1 AU, and the idea is to get two measurements of those line of sights, one at one time of year, let's say June, and the other one 6 months apart when we're at the extreme opposite of that orbit, like in January. So what we want to do is get two far apart distance values that we're taking these measurements of the shift of this nearby star with. So if we do a diagram, this is sort of what it would look like. Okay, so this is how we look at it from our orbiting around the sun and how we would make a stellar parallax measurement and how we get the equation that equates distance with this apparent shift angle that we'll look at. So the idea is we go around, it takes 365.25 days to orbit. Sometimes we're closer, sometimes we're further away. So if we started taking our measurement in June, so here we are, we're at a nice little observatory and we get some precise measures, and we're close to our furthest distance from the sun, aphelion, and we go ahead and we pinpoint this near star we want to look at, and we're trying to figure out the distance to. And so what we do is we draw a line of sight, we view this star, okay, with respect to these background stars. So here we have a nearby star. Here's our background stars. Okay. And then we wait 6 months later. We come all the way up here in January. And now we're going to measure the angle of this nearby star with respect to the background stars. Okay. We'll see this apparent shift. We'll see that in June, this nearby star will have a background that looks different than in January when we look at this nearby star against this backdrop of stars. And this is exaggerated just to simplify this because these motions are really, really tiny. It's very hard to see any little bit of motion. We can't see with the naked eye, but we can with good telescopes. The better telescopes we use, the more precise we get our measurements. Now, the idea is here, we know the average sun-Earth distance is 1 AU. So this is our AU distance. Okay? And this angle right here on either side is going to be your parallax angle. We call that P, or if we relate it to angular size, it's theta, okay, in radians. So P is our parallax angle, and then of course our distance to that star, okay, so our distance to that star, like here, D, or the D here is related to that parallax angle. And the relationship between these is that D is equal to 1 over P, our parallax angle. This is a big formula, and we'll do a few examples with it. So this is the distance to our nearby star based on this angular measure that we get, P, and P is equal to our parallax angle, and it's measured in arc seconds. Okay. So let's go ahead and take a look at some of these measures. And how this formula, look at the dynamics of this formula a little further. And its roots with angular measures. Okay. Looking a little bit more into this parallax angle distance relationship. Now, our parallax angle is measured in arc seconds. So again, if you go back and look at what we did with angular measures, we divide up the sky. So we take the Earth here and we divide up the cosmos, the heavens above us, into 360 degrees. 360 degrees making one complete circle around, also known as 2 pi radians, which is approximately 6.28 radians. Now we use radians instead of degrees when we mix it into equations with meters or other SI units. So when we're working with SI units, we have to convert to radians. We don't like to use degrees. But this handy little formula allows us to plug in this right in terms of arc seconds and give us a distance in terms of parsecs, because the parsec is based on an arc second. Okay? The parsec is defined as the distance measured from an object that covers 1 arc second of sky. So really important. So this parsec distance is going to be based on this arc second measure. So again, if we look at this, and here we are on the surface of the Earth, okay, and we know this is 360 degrees, okay, and you take a little slice, like a 1 degree slice, let's say this is 1 degree, okay, 1 degree can be sliced up into 60 minutes, which you take one of these little minutes and you slice that up further, and you get 60 seconds. Okay? Every minute equals 60 seconds. So we have 1 degree is equal to 3,600 arc seconds. Okay, and you could divide that even further. You could go into milliarc seconds, microarc seconds, which is what our sophisticated telescopes do now when they're measuring things like parallax. Okay, so we could divide the sky up even further than that. So basically, 1 arc second is equal to 1/3,600th of a second of a degree. Okay, really, really small measure. And for perspective, when we have 1 degree of sky, what does 1 degree of sky look like? Well, 1 degree of sky is 2 full moons. Okay, so half a degree, here's the moon, is approximately 1/2 a degree, or 31 arc minutes. Okay, you could cover it up with your pinky. Your pinky is approximately 1 degree across. Of course, this varies. We use a lot of finger measurements for approximations. Okay, so that gives you a size of arc seconds, an idea of how we use arc seconds. So we break up the degree into arc minutes and further into arc seconds. So when we're looking at stars, we're looking at really, really small amounts of arc seconds, high precision. So it really relies on the science of astrometry, which is the science of taking precise measurements like distance. Okay, so this is how we divide that up. So this is given in arc seconds. We got to make sure when we're working with this formula, the angles in arc seconds. D is our distance in parsecs PC, where 1 arc second is equivalent to 1 PC in distance. Okay, so something that covers 1 arc second in the sky is 1 parsec away. And remember, 1 parsec is equivalent to 3.26 light years. Okay, so we don't have any stars that close, but the nearest is 4.2 light years, very close. So we'll use this formula coming up. So this is a really important relationship. Now, the important thing to note is we know in this formula, we know objects, stars, closer, right, will have larger. So as far as getting stars distances, stars that are closer will have smaller distance value, larger arc second values. We like those. Those are ones that we could build on. And then, of course, stars further, the opposite happens. Smaller p, okay, and larger distances. Okay, and the question is, how far can you go? And how smaller than an arc second can you go? And for an analogy, you'll pull out a hair. Let's see if I got any available. And to give you some scope of what an arc second is, you could take the width of your hair at arm's length. Okay, that is what an arc second approximately covers. It's a really rough estimate, but that is the approximation. And something like the Hubble can see that very, very far away, a mile away. It can resolve images of the width of a human hair. It can resolve about a mile away, much more so. Okay, you can see fractions of arc second. All right. Okay, so a question that comes up is, how does this parallax distance relationship between parsecs and arc seconds relate to how we do angular measures? And this is the form that we do to estimate the size of objects, the diameter, based on how much of an angle it takes up, whether it be out in space, like how much of an angle does the moon take up in the sky? If we know the diameter of the moon, how much it takes up in the sky, we can figure out its distance. Or you can use any other 2 knowns to find the 3rd unknown. Okay, so how does this relate? Well, in this angular size equation representation, we have our angle that we like to have in radians, and our distance is what we want to find. But if we know our diameter in meters of an object, like if we knew the diameter of the moon, we could put the diameter of the moon in here, how much space it takes up in the sky, so it's about 1/2 degree, or more specifically, 31 arc seconds. but we would change that to radians. And the way you change any angle into radians, you would say degrees, how many degrees you have, times 2 pi, or 6.28, over 360 to equal your measured radians. Okay, you have to do that first. And then so you would say my distance would be my angle divided by the diameter, and I could find that. So it's the same idea on the relationships. The only difference is here what happens is D is 1 AU when we're measuring at 2 points on the Earth. Okay, so our distance is, well, we'd say 1 AU for measuring from here to here, from the Sun to one of the Earth's position. Okay, we would use that, and then we would put our theta in arc seconds right here, and then we could use that to find our distance to the nearby star. So this is really the same, this formula right here is really the same version of relating the size of an object, the distance of an object, and its angular size. Okay, this is angular size. And you could use radians or arc seconds. D is the diameter, size, and we use that in meters. And D is our distance. Okay? So, when our D equals 1 AU, our theta is in arc seconds, what we end up with is we have P equals 1 over D. Okay, these are virtually the same in that case, and that's how they relate. All right, so we'll look at doing some computations, and I'll give you a little quick brief history first. Okay, here's a brief little history, just to put parallax into context in astronomy and how much of a long way it's come since the early days. This started really out with the Greeks. So, there were some early Greeks that believed the Earth to be going around the sun. We got our first measurements for the circumference of the Earth from them. They did a lot of geometry, and they came up with the idea of parallax, but they weren't able to get the first measurements. Obviously, for them, it was probably quite a task without the aid of a telescope. So the early Greeks these were really the first attempts. And as we know, they laid a lot of wonderful geometric foundations that have got us a long way with our mathematics and our astronomy. Okay, and then what we look at next is the 1600s, the first telescopes really tried to measure stellar parallax. But again, as we know how tiny a little arc second is, the width of a human hair at arm's length, it is really hard to do. No success. Try, but no. And then we get to the first success, which is and I'll quote, don't quite remember the date, 1838. We had Frederick Bessel that did the first successful measure of stellar parallax. Okay, and what did he get to measure? He got the star 61 Cygni, which is not one star, but many. But the main star that he measured had a parallax angle found, or measured, I should say. Okay, approximately 0.3 arc seconds. Okay, and what that did was, and you could check the numbers for, this is our P. What that led to was a measurement about 11.4 light years, or 3.2 PC. Okay. And that was back in the day. So that was really done well. So the first star measured 0.3 arc seconds. We were able to get a distance of 3.2 PC. When you convert that to light years, multiply that by 3.26, you get approximately 10.4 light years. Okay, so now this got refined. Now we actually found this to be 3.5 PC slash 4, 11.4 light years away. Not bad, really good for back then. Okay, especially knowing that the early telescopes were really rudimentary, I mean by modern standards, and so we've really refined our telescopes. Our precision for telescopes have gotten better and better so that we're able to resolve tinier and tinier bits of arc seconds. Okay, and then nowadays, what do we have? Well, nowadays, the notable ones, now, I'm gonna go ... a lot has happened. Ever since Bessel made this first successful parallax measure, it just got built on. And now we rely upon satellites and space probes doing this. So there's a Hipparchus satellite. And I'm going to check my spelling on that. Hipparchos. Okay. And this was launched by ESA in 1989. ESA stands for the European Space Agency, and it has cataloged over 100,000 stars. Okay, so now we have over 100,000 stars with precise parallax measures, these nearby stars in the cosmic distance line, which is good. Then we can use those to build the further out distances. And then we have in 2013, we have Gaia, also by ESA. More, much more. Okay, and I think we got down to 10 micro arc seconds from my notes here. That is completely tiny, fractions of an arc second, pretty amazing. And then comes along Hubble with even more refinement, and then of course better and better. So really Hipparchus has set a higher threshold on stellar parallax and the values that we have. Okay, so just to practice some of these numbers, make sure that you are able to find the distance if, let's say, you had a measurement given to you, or you were able to measure this in arc seconds yourself, using fancy equipment, mind you. Okay, let's start with Proxima Centauri. So this is our closest star, as we know, typically quoted as being just over 4 light years away. So if it has a parallax angle of 0.776 arc seconds, can we find its distance? Or, you know, any other star? Well, we use our D equals 1 over P. And as long as our input is in arc seconds, it should whip out a value in parsecs, correct? So always look at your measures. So this is in arc seconds. Always ask yourself that. If it's not, then you have to change it. And maybe if it's a degree measure, and you have to divide it out and convert it to arc seconds. Okay. So what we have here is our D will equal 1 over get a value when you divide that out. I get 1.28 PC. That's my answer, 1.28 parsecs. Okay. Now, what is it going to be in light years? So, in light years, I do 1.28 PC times, I know that 1 parsec equals 3.26 light years, and I multiply 1.28 by 3.26, and I get a measure of 4.2 light years, the quoted value that we typically see. Okay. So that's Proxima Centauri. Now, what if I had a smaller arc-second angle, which I would expect for a star further away? Let's go ahead and do our star 2. In star 2, we're going to have let's go ahead and do Sirius. Now, Sirius is a binary star system. Binary stars are also used to help us find distances too, by the way. So let's do Sirius. And which one are we going to do? Sirius A or Sirius B? One's a white dwarf and one is a little more massive than our sun. Well, let's go ahead and do Sirius A. Okay. And Sirius A has a parallax angle that's been refined up to 0.379 arc seconds. And the question is, what is its distance? And let's find it in PC and in light years. Okay, because maybe we'll want to use light years for it. So again, we just go ahead and say the distance is 1 over P, and that will equal, in this case, what did we get? 1 over 0.0379, we get 2.64 PC. Okay, and then we go PC, 2.64 PC will give us how many light years? Well, let's multiply 1 PC by our conversion factor. 1 PC is 3.26 light years. And we cancel our PCs, and we get a value of 8.6 light years. Okay. So that's Sirius A. And some other challenges you could add here to it is you could relate this to the theta equals diameter over distance value. So we'll continue that on another video. But if we have theta equals d diameter over distance, can you convert that into arc seconds? And can you use your measurement in AU to find a distance? So this is a challenge you could do. And we will do some of these measurements in our angular size and measurements video. All right, I hope that helps you understand parallax.